All right, the final motif is going to be rearrangements. For this one, we'll just focus on one specific kind, and these are carbo-cation rearrangements. So remember, a carbo-cation is a carbon with a positive charge. And so you can think about a bunch of different scenarios. We could have a carbon that's bound to 3 hydrogens and has a positive charge. We could replace one of these hydrogens with a carbon bound to other things. So this R could be more hydrogens or more carbons or something like that. We could replace 2 of them. Or we could have a carbo-cation on a carbon that is bound to 3 other carbons. And so here we're going to learn some kind of deeper in knowledge here. And so when we go from the left to the right, we become more stable. And not only that, these have special names. So this is just called a methyl carbocation. This is called a primary carbocation because it only has one thing attached to it. We'll see this nomenclature again when we reach alcohols. This is called a secondary carbocation. It gets 2 with the degree symbol there because it's attached to 2 things that are basically not hydrogen or 2 other carbons. And then this is called a tertiary carbocation because it's attached to 3 things. And so tertiary carbocations are much more stable than methyl carbocations. You essentially can't form a methyl carbocation, and really even primary carbocations are not realistic. So these 2, secondary and tertiary, are kind of realistic to form. Methyl and primary, not very realistic to form. The reason that secondary and tertiary carbocations are more stable than other carbocations is due to something called hyperconjugation. And so what's going on here is we have a carbon with an empty p orbital. That's our carbocation. And then if we think about its bond to a hydrogen, right, that's going to be kind of a sigma bond here. And so that's not really going to help out our empty p orbital whatsoever. But then if we have another carbon attached, right, we have a hydrogen here, and then a hydrogen here, and then a hydrogen up here with our overlapping sigma bond. What can basically happen is some of these electrons from this bond can be donated into the empty p orbital. And this is called hyperconjugation. The end result, and really all you have to know, is that tertiary carbocations are more stable, secondary carbocations less stable, but still possible to form. Primary and methyl carbocations not very stable at all and highly unlikely to form. But let's say you did form a primary carbocation, right? So we've got this primary carbocation. This is not going to be very stable. And so what will actually occur is a rearrangement where the carbocation will now become a tertiary carbocation. That is overall relatively stable. And so again, you want to think about how did we get from the left to the right? Well, if you think about it, we have this hydrogen here, and in this carbon, there's no hydrogen here. And same thing here, you have 2 hydrogens here, whereas here you have 3. So one of this hydrogen with its bond moved over. And this is what's known as a hydride shift. So basically what happens is this bond here basically moves over with this hydrogen to give our product. So again, this is called a hydride shift. A hydride is an H minus, right? So it's a hydrogen with 2 electrons. And so this can commonly occur. Here's another example of something slightly different. So again, you want to maybe go ahead, pause the video, and think about how did we get from the left side to the right side. Well, if you notice on this left side, this carbon has 3 methyl groups, where on the right side it only has 2. And this one only has 1 methyl group, and now it has 2. So we had this methyl group move to give us our product. And this is called, similar to a hydride shift, this is called an alkyl shift. Because instead of a hydride moving, you have an alkene or alkane moving, an alkyl. And again, this happens because this is a secondary carbocation, whereas this is a tertiary carbocation. So your carbocation is always going to move towards the most stable compound. And not only is it going to move to the more stable one, it's going to move to the more stable close by one. So for example, in this compound, we have this positive charge, and then we can think of this 2 different shifts occurring, right? We could think about this shift occurring, or this shift occurring, right? If we think about where our carbocation is going to end up, the orange one is going to be more likely, because it will result in the more stable carbocation. The other shift is going to be much less likely. And think back to our resonance structures. Resonance is also going to stabilize charge. So this is what's known as an allylic carbocation. So this carbocation is right next to this lone pair, and this is stabilized because of resonance, right? This lone pair, or this positive charge, is spread out more evenly, and so it is more stable. So keep an eye out for carbocation rearrangements or alkyl shifts, right? Or hydride shifts.